Okay, short continuation of the previous video. We had gotten to the point where we were interested in this equation, dp dt equals kp. I was looking at the case 0.02, but we want to really solve it in general. We found that dp dt equals p gives you e to the t. If you change that constant k in front, you don't just put that in front of e to the t. That doesn't work. But if you put it in here, in front of the t, then that does actually work. And so let's see. If I have p of t is e to the kt, where k is a constant, like the 3 in this example, then the derivative of that, the derivative of an exponential is itself, but times, the chain rule is always in force, so times the derivative of kt, which when k is a constant is just k. Okay, so that's what we started with, times that constant k. And so this solves this equation, p prime equals kp. So let me say a minute about the idea here. It's a very different kind of idea from solving equations in algebra in some ways. In algebra, the mystery quantity is a number, and it's represented by a letter, but in the end, the solution is just going to be a number. Or maybe 1 or 2 or 3 or 4 numbers or something like that, if there's more than one solution. Here, the mystery thing is a function. It's a far more complicated object to be your unknown. And that's a pretty high level of sophistication, in fact, that we get to when we start thinking about differential equations. It's not going to bother us too much, but it's lurking in the background. That we have an unknown function, p, and we want to know what it is, and what we know about it is just that it has this property that its derivative is a certain multiple of itself. And so that's a very common thing. Is we have a differential equation basically is a statement about a mystery function that says something about its derivatives. It gives some sort of relationship between its derivatives and itself. It might involve the second derivative. It might involve p squared or something like that. There's all kinds of different flavors. But it's some fact, some equation, some fact that's true about the derivative of p, about that unknown function. Here, we had this kind of equation. P prime is a certain constant multiple of itself, and we've found at least one solution to that. And then there's a big question as to, are there other solutions to that? Well, let's go ahead and address that real quick. Here, when we actually did a false guess for dp dt equals 3p, a lot of people guess, oh, I'm just going to triple the e to the t. But that doesn't actually solve the new equation. It was actually a solution to the old equation. What is a function whose derivative is itself? Because if we took the derivative of 3e to the t, the 3 just hangs out. It's not like a new 3 is created or it's destroyed. It just hangs out, and so you've got another function whose derivative is itself. Well, did this have to be a 3? No. This could be a 7 or a minus pi or any constant, and that's going to give you another function whose derivative is itself. Well, same thing's going to work here. Suppose I try to make this a little more complicated, and I take p of t is, let's put in really explicit numbers. Let's say 7 e to the 5t. Take its derivative. P prime is going to be 7 e to the 5t times 5. Well, that's still what you started with, times 5. So what differential equation does that solve? P prime equals 5p. That would have been true without the 7 there. It's true with the 7. It's true with the 17. It's true with 117. It doesn't matter what that number is. Since it isn't affected by the derivative, those all solve this differential equation. So what we can do is we can say, oh, this is actually just anything we want. And we have a notation for that already, an arbitrary constant. So if you have p of t is any number c times e to the kt, that solves this very, very important, the most important differential equation, p prime equals kp. This is the kind of function that has a constant relative growth rate. And that's why in a few pages ago, I said there's this blank, what kind of growth? As opposed to linear growth where dp dt is constant, that's just a straight line. It's exponential growth that has this constant relative rate of change. And so there's, just take any number, some whatever number c you like, times e to the kt, that's going to have constant relative growth rate equal to k. So the thing that goes in front of the k is exactly this guy. So those are both that relative rate of change. I was saying growth, that's if it's positive. Again, it's decay if k is negative. We'll explore that. So back to our example, that population example we started in the first video, k was 0.02, 2%. And so P of t equals any number you like times e to the 0.02t is going to satisfy or solve, same thing, p prime equals 0.02 times p. And so this is the kind of model we're going to have for a differential equation and solving it. We have some fact about the function. I'm not telling you what the derivative of the function is. That's a very simple version of differential equations, but that's not what's happening here. I tell you that this has this funky property, that when you take the derivative of this mystery function p, it is 2%, 0.02 times what you started with. But I don't tell you what p is or what p prime is directly. But what we figured out, basically by educated guessing and being familiar with certain properties of functions, is that it looks like that p of t has to be some multiple of e to the 0.02t. We'd like to nail this down a little bit better and make sure that there isn't some other function that has this property. Maybe there's many functions that have this property. We've never seen anything else but e to the t that behaves so simply when you differentiate it. We'd like to be sure about that, and we'll have a way of being sure about that. But it turns out this is really the only thing it can be. We'd like to figure out what's the role of big C here and how to find that. That's not too hard. And we're going to look at lots of other kinds of differential equations, not just the derivative as a multiple itself, but any function, any relationship between the derivative and the function, and see how many of those can we figure out what the solution says. So there'll be a lot to say about that, but I think that's a good place to stop the introduction.